Hello and welcome to a new episode of Today You Learned. So today I would like to show you my take on a known vulnerability and a known but recent exploit of that vulnerability or vulnerabilities. It's called Bitpixie and it's in fact a software-based BitLocker bypass. BitLocker is a volume encryption or a disk encryption utility by Microsoft. It is enforced on a lot of systems. However, recently, last 3 months, new exploits have been created to bypass that BitLocker encryption. It's based on these two CVE codes, a very short introduction. So what is the issue? The issue is that the BitLocker encryption key, called the VMK, is in memory even after being unlocked or recently unlocked. The unlocking in most circumstances happens automatically, so no user interaction, which means that the Windows bootloader, which is signed with a certificate, loads the key from the TPM chip and then uses the key data to decrypt the volume master key, the VMK, loads that VMK in memory and then continues to use that VMK to decrypt or unlock the volumes themselves. What is the exploit that I want to show you? We want to boot into a Windows pre-boot environment, so on the target itself. We want to take a backup of the BCD, so the boot configuration data, which is actually in a shared volume that is not encrypted, and even a FAT32 volume to be correct. And then after creating that backup, we can reuse that backup to continue to boot via the network, so a network boot with this BCD into a Linux environment and then scan, using that Linux environment, scan the memory for that clear text volume master key. When we have that VM key, then the exploit is more or less done, but then that's where the fun starts. So what is that VMK? Very short, it's actually a chained event. We have our Windows volumes like C, D, E and so on. When you enable BitLocker, these are encrypted with volume encryption keys or full volume encryption keys. These keys are encrypted and stored in the metadata, so at the beginning of the volume. So these keys are encrypted. How can you decrypt them? That would be with that volume master key, which is 16 or 32 bytes. That's the one we actually want. This key itself is also encrypted and also stored in the volume metadata at a static offset, a certain place, so that the bootloader knows where to look for it. And of course, that VMK key itself is also encrypted, needs to be decrypted via something called a key protector, which can be a password, an external USB drive that has a file on it, even a floppy, or a hardware-based TPM. So the most common, of course, is that last one. So once we have that VMK, all volumes on that drive can be decrypted. So how does that look like? Like I said, we have our data right here. We have our two, for my demo as well, we have our two BitLocker encrypted volumes. And then in case of UEFI, we always have a UEFI partition at the beginning, which, as you can see, does not have a letter, but is also not encrypted. So this one is always available to anyone that wants to look at it via network boot or otherwise, USB boot and so on. So time to dive into the demo. So let me see if I can switch to the camera. So we have our target. It's just booted for ease of use. So we have our very recent Windows system right here. This is our hacker system. So what I did is actually I created or took a Raspberry Pi. It's even an older one. This is Raspberry Pi version 3, I believe, or 3B. So this Raspberry Pi, I have mounted a very small screen just for the display and for showing messages and things like that. So I will attach it via the network right here and then try to hack the system, right? So this is the system that has bootlocker enabled. The normal circumstances would be that the system is turned down, shut down, and we find it somewhere. Then we can enforce it via trying to boot and failing to boot. We can force it into the system recovery mode, Windows recovery mode. If we reboot 3 times during the normal Windows boot, then that's what happens. So to force or to convenience ourselves a little bit, I will now do something called a shift reboot. So if I press Windows X to have that little menu right there, if I go then to shutdown or restart and I go to restart, instead of pressing enter or clicking with the mouse, I will press Shift and then click with the mouse or just enter, like so. So now Windows will just reboot, like I told it to, but it will reboot into the recovery mode. Okay, while that is doing, we will boot our system. That is being done via a Windows or just a USB drive or a USB connection. It's a simple micro USB connection because it's an older version of Raspberry Pi. So as you can see, it's plugged in right now and it's booting. It will just boot into a very default Raspbian environment with I believe it's Debian 11 or something like that, or Raspbian 11 installed, and we will have a small desktop on it, right? So while this is booting, I'll try to put it in view. I will already plug in the network right here, like so. So one side of the network connection is already connected. So while that is booting, I will actually already show you what we can do on the Windows side. So this is the Windows recovery environment. From here, one of the prerequisites is that we should be able to boot from the network. So that's something that we can verify via user device. If network is in the list, which it is, then it's good to go. If that's not the case, we have to reboot into firmware, so the BIOS environment, and there we can enable network boot. In this case, that's already done. Of course, this will not work, enabling network boot, if the BIOS has a password. So we might have to do a BIOS reset and so on and so on. But for this case, it's already done. So we can move into troubleshoot, because before booting the network, we have to create a backup of our BCD. So I go into troubleshoot, advanced, and then we go command prompt, into command prompt. So this is a command prompt that should start up from the Windows recovery environment, so not the Windows normal command prompt. It asks me if I do have a recovery key, because the command prompt is much more useful, of course, if you have access to your hard drive, which we do not, because it's locked by Bitlocker. So we can actually skip this drive. Skip means still open up the command prompt, but do not use do not unlock the BitLocker drive. We do not have the keys, so I do not have access to the BitLocked drives right now. But that's not big of a deal. It's no big deal. So what I have to do now, let's see if I can make it a little bit more visible. Sorry, like this. Okay. So the old school way of zooming in, just closing the camera, of putting the camera a bit closer to the display. It's also in QWERTY. I hope it's more visible if I put it like this. So the first thing I have to do is actually to connect the Raspberry Pi. So there we have our Raspberry Pi. So let's connect the Raspberry Pi via the network to the device. And now, one thing I have to do on the Raspberry Pi, I didn't enable it by default, you can enable it by default of course, is to create a DHCP server. I have one script that is actually on the desktop, the Bitpixie script. So that Bitpixie script will do several things. Let me first try to start it up, and then I will show you. So there we are, it's already booted. See if I can focus it a little bit. Yep, there we are. You might detect it has something like DNS mask installed. So DNS mask does actually do several things. Very simply, it creates something called a DHCP server, which means handing out IP addresses and IP related data, subnet mask, and so on. The second thing that DNS mask does in my environment is to create a TFTP server, which is a requirement for network boot. But first, my Windows system right here does not even see a network adapter. That's because it's not initialized yet. So I need one command. So what happens now is that you might even see the lights flickering here. It will initialize the network adapters that are detected on the Windows system, in the Windows recovery environment, and even starts up a DHCP client. So now if I do my IP config once more, you can see I have an IP address. So the next phase, what I also enabled on this Raspberry Pi, is something called an SMB server, or a Windows Share service. So I can actually connect to that Windows file service and copy files, backup files, or run files. And I will actually run a file first. You can actually see in ipconfig the gateway, which is the IP address of the Raspberry Pi. Then this is something that tends to happen. We have to wait a little bit. But what I will try to do, or trying to do, is that I'm trying to run a bat file that is actually on the Windows file share of the Raspberry Pi. So there's a shared folder called PXP. In that shared folder, there are some files, and one of them is a batch file that I'm trying to run. Of course, it works better if you don't make any typos, but okay, here we are. So that batch file, I can actually even show you what it does. It actually creates a backup of our boot file. So there we are. So bcd edit is a command to connect with the Windows boot file. It creates a backup and it configures that file, as you can see right here, recovery enabled, recovery sequence. It enables the Windows boot environment, and it actually allows to use this boot file, from this laptop. We can use this boot file now to load, for example, shim x64, which means we can now boot Linux recovery images instead of having to force the Windows recovery on it. So this allows us, so we only need to mod this BCD to allow us to actually launch a Linux environment. That's the idea. A Linux environment while still using the original Windows bootloader. And by using the original bootloader, it will actually load the Windows Bitlocker VMK key in memory. Not unlocking the drives, but still loading the VMK in memory, so speaking to the TPM, loading it in memory, which we then can retrieve from that memory. So let's do that now. As you can see, my script tells please close window, continue the PXE boot without rebooting Windows, so that's important. Close. So now we can go back to the device, launch the EFI boot. We can actually even monitor it. Let's see how that looks like. As you can see, we see DHCP requests, the specific DHCP configuration, the DORA, the DHCP discovery, the offer, the request, the acknowledgement. I try to zoom in a little bit more without disconnecting the network. Let's see, like this. There we are. As you can see, it is trying to now load. It has loaded Bitlocker grub, so which is the Linux bootloader. If now it focuses, we have a very good view. Still trying, maybe it's too close now. But in any case, it's now loading the Windows bootloader from the TFTP server together with grub. And what we are waiting now for is actually the TFTP command, or the TFTP is now loading something called the init ramfs, or the initial file system, ramfs file system, that is to be loaded into memory, into the RAM memory of the laptop. So this would be the entire Linux directory or file system that it will need to run from memory. So that's why this takes some minutes. As you can see, we have to wait a little bit because it takes up, well, in my case, about around 200 megabytes. So it takes some time to load or to copy 200 megabytes from the Raspberry Pi onto the laptop. But it is booting into a Linux system right now. There we are, where we have still access from kernel, of course, access to memory. So there we are. In theory, I could now even shut down the Raspberry Pi because we are running from RAM. However, of course, why not? Let's leave it enabled right there. Maybe put it like this. There we are. So that's the very simple Linux environment called Alpine. I will log in, very difficult. Root. There we are. It has detected that there are, maybe close in a little bit, that there are two volumes that have been encrypted with Bitlocker, two partitions or volumes, and both of them have the same VMK, not the same volume encryption key, but the same volume master encryption key, the VMK. So I will just run the command run exploit, which will scan for the memory and then do some other things. I'll first run the exploit. I will take the first partition, which I know is the C partition. It usually is, and that's the most interesting partition, of course. So that worked. So it has actually, it knows how that VMK key looks like. It's usually a 32-bit or 32-byte long key, so pretty long, as you can see in the memory in the center of the screen. It has looked for that pattern in memory. It has found several options, but the first one was a version mismatch, so that was not a correct key, and then the other one seems to be correct. It has then created a backup of that file, stored it on /root/vmk.dat, which is not a good place, because if I close my laptop or shut down the laptop, then that key is gone. So it is a good idea to copy that key onto a thumb drive or just take a picture from that key. So that will be this key. We take a picture of that. So if we shut down the laptop and we take out the hard drive, for example, we can just mount that hard drive to any Linux environment and then use the default Bitlocker command. That's a part of Linux if we install it, of course, together with that VMK file or key to unlock any volume on that entire drive. However, that's exactly what the run exploit command has done for me. It has already created that backup and used that file, that VMK key, to first unlock the partition with Bitlocker and then mount the unlocked partition into /root/mnt, which is what you are seeing right now. And then it even did an ls just to show me that I can have access to the full file system. Okay, I tried to make it a little bit better. So after unlocking the hard drive, this is what we see, of course. We have our file system of the C drive. Then to this environment, I actually added a couple of things. One of the things that was already there is called CHNT passwords, or PW. So this is actually a tool that allows to change a password of a user on the hard drive. It's useful, but it of course changes a password, and I don't like to change anything on file systems for several reasons. Of course, production is not a good idea to change data on hard drives. So luckily I created a framework that actually allows to decrypt credentials and other sensitive data in place, and this framework is built on top of the default Windows encryption library called the Data Protection API, TP API. The framework that I've made is called Diana. So Diana.py is actually also installed in here. So this is actually a library of scripts that uses the native implementation or a native implementation of the Data Protection API to decrypt credentials and other things from a hard drive. So I will not go over every single script that you can see here, of course, but I wanted to show you one or two, of course. A separate video will be created on Diana in the future. So let's maybe look at the general scripts at the top. We have our generic script called registry decryption. So what this script actually does, if I launch it like this, just to look at the help, it allows us to read out 4 registry hives from the hard drive, parse them, and see some juicy details on that registry. So if I do that, it looks like this. So what do we see right here? We see that we have our operating system details right here, which is pretty up to date when it was installed. But we also see the list of local users. Okay, no big deal if there are any secret questions. And then we have the local users with their hashes. We have, of course, the 3 default Windows users that are also default disabled on Windows clients. And then we have 2 hashes for each of these users. We have the first hash right there, which is called an LM hash, which is empty in all modern Windows systems, including for active users like my user. And then the second hash, which starts with 31D or 31D6, is called an NT hash, and 31D6 means that it is an empty hash. So there is no password configured for the first 3 users, but there is a password for the 4th user that you can see right here. So this is an NT hash that we can also use for other attacks like pass the hash. Then of course the script also reads out other details from the registry, like domain cached credentials or domain cached hashes, any accounts that uses Microsoft Live or other accounts that use Entra ID or Azure ID, and it also detects a default Windows login, but it's not a normal one. It's not one that I actually configured, so my system does not have a Windows default login. However, it seems to have been configured by Microsoft automatically or by Windows with something called the automatic restart sign-on, the ASRO. This is actually something that Windows often does when rebooting itself, especially if there are any updates to be done, because it allows to work faster. It actually stores sensitive data in the registry to allow Windows, before you enter your password to log into Windows, to actually in the background already log into Windows, so Windows is unlocked without you entering any passwords, and then do certain things like starting up services or unlocking drives or something like that, or for volumes. So for this to work, it actually stores a very critical piece of information into the registry, which is not the NT hash, which we already have in the registry, of course, but it is the SHA-1 hash of the exact same password. So we have 2 hashes for the same password. What's so special about this SHA-1 hash? It is special in the way that this SHA-1 hash is actually the one that is being used for encrypting any user credentials. And a Windows system is filled with user credentials. All your credentials, passwords in your browsers, Edge and Chrome and others, all your cookies in that same browsers, Edge and Chrome, your credential manager that is in part of Windows, credential vault, your Wi-Fi passwords, and many others are all encrypted using Data Protection API, which uses the SHA-1 hash of your password to decrypt. That's the reason, if you look at the passwords in your browser, that it asks you to confirm your password or your PIN code or whatever you use to connect to Windows or to log into Windows, because it uses that to generate that SHA-1 hash or verify the SHA-1 hash and to decrypt your passwords. So what can we do? Well, let me first maybe retrieve or store that SHA-1 hash into a file so I can reuse it later in my comments. So I will just rerun my registry right here, my registry decryptor, and as you can see, if I do it like this, as you can see, I just read out the 5A1, so the hash itself, so I only have that, and then I will actually now store it into a file somewhere in the temp folder. So in the temp folder I create a SHA-1 hash, so if I verify that, I should be able to see the same hash. So that hash, as far as it's clear on this picture, is actually the SHA-1 hash of my password. So now I can actually use that SHA-1 hash to decrypt certain credentials. Maybe let's have a look at my browser. So it's also important to note that I am in the root of the C drive. So if I want to see details of my browser, I have this script called browser decrypt. If I look at it without anything else, it expects me to at least provide something called a local state file, which is actually here. So in the users folder, I have my name, I have the app data local that I can actually abuse, and then local, and then we have, for example, for Chrome, we have Google, of course, and then Chrome, and then the local state file is actually inside the user data folder, local state. So what do we see here right now? It's trying to decrypt, but it's not fully able to decrypt because I haven't provided any user details. That's all in the text here. It needs certain files called master keys, and then it needs my hash to decrypt the master keys, which in turn are able to decrypt the Chrome master key. And then that Chrome master key can be used to decrypt cookies and passwords. So first I will actually specify the hash, right? So I will cut out the hash, cut SHA hash. So now we have -a to just specify the hash, right? Like this. And now I need to specify, which is the last part, I need to specify the master keys, which are always in the same location, which is app data roaming, and then Microsoft, protect, and then you have the system ID, the SID of the user. That's the name of the folder where all the master keys are stored. If I do it like this, you can actually see the master keys. It will automatically, if I specify the folder, automatically find the right master keys and then use the hash of my password to decrypt the master keys. And with the decrypted master keys, it will try to decrypt the Chrome, the browser master key or encryption key. And then with that Chrome encryption key, it can actually decrypt passwords, which are in the file login data, or cookies, which are in default network cookies. So as you can see, it has found the two encryption keys, because newer versions of Chrome now have two encryption keys, the master encryption key and an application aware key, the ABE key. So as a last phase, I can specify, for example, the Chrome cookies, because hackers are of course more interested in cookies than in passwords nowadays. So where can you find these cookies? They are in Google, Chrome, user data, default, network, cookies, right? Let's have a look. It will actually do the same. And as you can see, it has found, you can see it on this line, it has found 99 cookies in the cookie file. It's just a SQLite database file, and then it now regenerates, it already had it, but it's now redoing the decryption of the browser master keys, and then it can use or will use those browser master keys to decrypt the cookies, which has worked for 99 out of 99 cookies. And I will not, of course, show them with -v, because that would be an invasion of privacy. Then very quickly, let's dive back to the presentation. Why? Because I have one more slide. How can you verify if you are vulnerable for this boot, the Bitlocker bypass? There are three options, or three things that you can verify. So you can run this command right here, the manage-bde command, as administrator on your logged or Windows that is booted, to verify if PCA validation is enabled. If it is, then if you see a digit 4 in the list that is being shown by running this command, then you are safe and the Bitlocker bypass will not work. Second option is, of course, the certificate on the Windows bootloader can be replaced. That's a lot harder to do because you need an update and a manual configuration, but you can verify it with this command. And then if 2011 is shown, you are vulnerable. If it's another one, if it's a newer one, then you are fixed. Thank you, and keep learning.